Good morning. Happy Friday. Thank you for being here, and hope you have a great weekend. Monday, when I see all of you at 1:10, the couple things that are due. Titration calculations lab will be up. The rough draft of the class presentation will happen. Remember, the rough draft means at least 2 typed pages. More is fine, but at least 2. The cover sheet, which is in the syllabus, and the class presentation, frequently asked questions, should go on the front. And also include 1 abstract from a science peer-reviewed article with the citation. Your final paper will need 2, so you can include both, but just 1 is all I'm looking for, or something like that. Problem set number 3 is up, and then after that we'll take quiz number 3 before going into lab, doing the acid-base titrations lab, where we're actually going to do some titrations, not just talk about them and get your calculator's money worth this week. Questions? Any of that? Does anybody need a printed copy of the companion? A student bought like 10 versions, and I have like 10 in my office. Does anybody want one?
Sure.
Yeah. Anybody else? I've got a whole bunch. All right.
I know I've got one.
Okay, cool. Yeah. Lana? Okay, good. All right, cool. Well, if anybody watching this or not watching this wants one, let them know. I've got some in my office. So. All right. The Henderson-Hasselbalch is super cool for buffers, which is what we're talking about right now, but it can also be used in the titrations, which we'll hopefully talk about today. And at the end on Wednesday, I left you with these 2 equations, which do look a little funky at first, I'm not going to lie. However, it's so much nicer than what I call the double ice equations. So instead of going through a calculation where you're having a strong acid or a strong base attack a buffer, that would be the first ice. Then you figure out how much acid and base is left, and then you do a second ice to figure out concentrations of hydronium, etc. This is one-stop shopping. You have to use moles, all right? You can't use moles per liter with this version of the Henderson-Hasselbalch. With the actual version, you can use moles or moles per liter, but here you have to use moles. And as someone that has done a lot of these, man, this is helpful. pH equals pK plus log. It's always base over acid, and you always want to figure out how much base is left over and how much acid is left over. So if you have a strong acid, it attacks the base, so the base amount will go down. But as much as the base is used up, that conjugate base makes more weak acid. And it's the same number, the same moles of strong acid will add to the weak acid as well as taking out the weak base. If it's a strong base, it's the opposite. The base attacks the weak acid, so it goes down, but as much as the acid decreases, the conjugate base increases. So that's the only kind of thing, and it is really helpful as we'll talk about. Now, before we do anything else though, I wanted to kind of revisit this kind of question. We've got a buffer, we're adding a strong base. What's going to happen to the pH? And before you think about math or Henderson-Hasselbalch, what does a base do to a solution? Does it make it go up or down pH-wise? Up, that's right. So I want you to keep that in the back of your mind, all right? If you add a base, it's going to make the pH go up. If you add an acid, it should make the pH go down. Now maybe it's 0.000001 pH units, but it will make it go up in this case or down a little bit. So keep that in the back of your mind while we go through these things. Okay. Here's pictures of Henderson-Hasselbalch. Woohoo! Selfies. Anyway, let's say we wanted to make a buffer, all right? And this is used a lot in biology and chemistry and all kinds of stuff. But let's say that we want to make a buffer with a pH of 4.30, so a little bit more acidic than basic. And the hydronium would be 10 to the minus 4.30, which comes out to be 5.0 times 10 to the minus 5 moles per liter. When you're picking a buffer, you ideally want the hydronium to be close to your Ka and or your pH close to pKa. Because remember, good old HH, pH equals pKa plus log base over acid. And the most important part usually is pH and pKa being roughly equal, all right? You'll fine-tune the pH with a base to acid ratio that makes it exactly what you want. But if you can at least start with a Ka that's close to the hydronium or the pH close to pKa, you're good to go. And in the literature, I'm seeing more and more acids listed, not so much by Ka, but by pKa. That's because usually people have a specific pH they want their buffer to be at, so you can then pick up pKa, which is close to the pH that you're looking for. So let's say Donovan and I want to make a buffer, pH 4.3. We go to the stockroom, and it's always inevitable that you don't have everything you want, but we do find these 3 buffer possibilities. All right, so these are the chemicals we have. Now, when it says HSO4 minus, SO4 minus, that would mean that we would find, for example, a sodium hydrogen sulfate and a sodium sulfate chemicals, all right, something like that. But we don't really care about the sodiums, we just want the active ingredients. So this would be one set of buffer we have, which again is a weak acid and its conjugate base. We also find acetic acid and acetate, and we find hydrocyanic acid and cyanide. And we do a little research, we find these Kas and these pKas, and again, you want to find ideally a pH close to your pKa or a hydronium that's close to your Ka. And so hopefully you can see that definitely the acetic acid acetate would be the right answer here. 4.74 is close to 4.30, and 1.8 10 to the minus 5 is kind of close to 5 times 10 to the minus 5. If we pick this one, it would probably be too acidic because the pKa is a lot less than what we want in terms of pH. This one right here would be more basic, all right, be closer to 9.4 for pH. Questions? All right. Now, if we have equal moles of base and acid, pH equals pK plus log base over acid. If the moles are equal, we're going to have a log base 10 log of 1. Does anybody remember what a base 10 log of 1 equals? 0. That's right. Yeah. No, it's all right. If you don't know, it's all right. Like, never what I had for breakfast or dinner last night, for that matter. But anyway, if the moles are equal, log of 1 is 0. So initially, pH and pK would be equal if that's what you want. So we want to have a pH of 4.3. We're going to get 4.74 if we're equal. So the question is, before we do any math or anything, do we want to end up with more base relative to acid, more acid relative to base, or equal acid and base? More acid than base, right on. Again, this is what the pH would be if the moles were equal, all right? But we want 4.3, which is more acidic, all right? So at the end of the day, the base-acid ratio, we want to have more moles of acid than we're going to have base. Now, if we wanted a pH of, 5.1, that would be more basic of a pH than 4.74, and then we'd have more base than acid. So when you're thinking about buffers, this is really useful. Like, we want a more acidic pH than if they were equal, so we're going to have more acid relative to base. How much more acid relative to base? Excellent question. What you can do is set Ka equals hydronium times conjugate base divided by acetic acid. And if you rearrange this for hydronium, you get hydronium, which is this number, which is what we want, acid over base times Ka. So this is the ratio that we're looking for. It's the ratio of the acid to the base. So you can see here that what I'm basically doing is taking hydronium and dividing by the Ka, this divided by this. And sure enough, we get this ratio 2.8 to 1. All right, the number in your calculator comes out to be 2.8, but the hip chemist would know then that it's acid over base. So what this means is that for every mole of the base you add, you want 2.8 moles of the acid. So if we had 10 moles of base, we would want 2.8 times that, or 28 moles of acid. So rearranging this equation will allow you to find the ratio, and then you can go from there. So we want a ratio of 2.8 to 1. And let's say that we have 0.1 moles of the base, which is the sodium acetate. We want then 2.8 times this number. So 2.8 times this is 0.28. That's how many moles of the acid we want. And if we do that, we should get our desired pH of 4.3. Now, there's different things you can do with this, all right? And some people really, really dig this. Another way you could do the same problem is to use Henderson-Hasselbalch, all right? You know I'm the Henderson-Hasselbalch guy, by the way. Prop that back on. pH equals pKa. We want 4.3. pKa is 4.74. So 4.3 minus 4.74 comes out to be minus 0.44. And if you want to get the base to acid ratio or whatever, 10 to the minus power is how you get rid of those things. You end up with 10.-44.36 equals base times acid. And you can get the ratio that way too. So whichever way works for you is awesome. But at the end of the day, just remember, if pKa is 4.74 and we want a pH of 4.3, we're going to have more acid relative to the base. So some way you can then calculate this ratio of 2.8 to 1 would be good to go. Questions? So here's an example of a problem you might see. We're preparing a buffer. We've got 8.4 grams of sodium hydrogen carbonate and 16.0 grams of sodium carbonate. Remember that carbonate has less hydrogen than hydrogen carbonate. So that means hydrogen carbonate is the weak acid, and the thing with less hydrogen will be the base, the weak base, the conjugate base. So the equilibrium we're using here is thanks for playing, hydrogen carbonate, there we go, plus water, making hydronium plus carbonate. And the question is, what will be the pH? So this question, to me, screams Henderson-Hasselbalch, all right? Because it's a buffer. You've got a weak acid and a base. You've got an equilibrium. You know what the acid is in the conjugate base. pH equals pKa plus log base over acid. So if you gave me this problem, I would recognize it as a buffer problem. They're conjugates of each other. I would turn both of these grams into moles. Moles of the carbonate on top divided by moles of the acid on the bottom. No reason to worry about volume because that's the nice thing about HH. I would look up the Ka for the hydrogen carbonate ion in problem set 2 or 3, turn it into pKa, and
to prepare our buffer solution, we first weigh our conjugate pair, 16.0 grams of sodium carbonate, the weak base, and 8.4 grams of sodium bicarbonate, the weak acid. We dissolve these solids in 100 milliliters of water. The final buffer solution has a volume of about 120 milliliters and a pH of 10.5.
If you have nothing else better to do this weekend, don't throw tomatoes at me, please. You don't have to really do it, but if you don't, this would be a cool practice problem, all right? You know what the answer is. See if you can get to this. Turn both of these grams into moles. Look up the Ka, turn it into pKa. pH equals pKa plus log base over acid. And if you get 10.50, bam. Questions? Now that we've gone through the buffers, now we can really approach, which is the ultimate goal of this section, which is being able to find the pH of any acid and base coming together, any combination. So like we saw in lab this week, we're looking at 4 types of titrations. And these 4 types represent 99.9% of the titrations that are done commercially and for business and stuff like that. We're not doing weak acid plus weak base combinations. Those are just troublesome. And if you can figure these out, you can literally find the pH of any system, which is really, really cool. So now that we know about buffers, and we can start talking about the other ones. And in lab, I went over pretty good how the strong acid, strong base stuff works. We'll go through that again here. But now when we get to weak acids and weak bases, we'll see how that Henderson-Hasselbalch can come back to help us out again. All 4 types of titrations are split into regions, all right? We'll have the initial point, we'll have an equivalence point. Everything after initial and before equivalence is the pre-equivalence region, and everything past equivalence is going to be the post-equivalence region. So you need to know what region you're in, and it's all about the moles. Equivalence means the moles of what you're adding in the burette are equal to the moles of what you started with. The titrant, titrant's this one, analyte's this one. Means you don't have any of the burette volume added in. You have just the stuff you're starting with. Here you have more moles of what you started with than you have moles of the added stuff, the titrant. And past that, then you have more moles of the titrant than you have moles of what you started with. So knowing how this works is really cool. And why I did buffers first is that the pre-equivalence region for a weak acid, strong base and weak base, strong acid is best described through Henderson-Hasselbalch. So now that we've got that under our belt, woohoo, let's do some calculations. Exactly. Yeah, you're just singing on a Friday when it's nice out. I'm singing that song too, for what it's worth. No, I'm excited by this titration. All right. Some hints on titration calculations, all right? Remember that those crazy strong acids and strong bases, no Kas, no Kbs, 100% product favored, single arrow, no equilibrium going on. They annihilate whatever their opposite is around them, all right? But that's quite different from weak acids and weak bases. If they're conjugates of each other, they hang out. They don't mind. Ammonia and ammonium, base and acid, they'll hang out together. Acetic acid, acetate, no problem. However, you put ammonia and acetic acid together and it's a different story. And that's why we're not talking about weak acid plus weak base titration, stuff like that. Also, if strong acids or strong bases come in, they attack whatever the weak system is. The weak systems create their conjugates, all right? And that'll have an effect on the pH we'll see. If you are a scientist discovering a new weak acid or weak base, you don't have a table of Ka and Kb values, but you can find those values from the titrations, and that's going to be something we'll talk about here in a little bit. The half equivalence pH is really important if you have a weak acid or a weak base that you're titrating, all right? Remember, strong acids and strong bases don't have Kas and Kbs. That are useful anyway. But the weak acids and weak bases, definitely, and you can find it through a titration. And along the way, we'll remember that Kw is the only K value I want you to know, 10 to the minus 14. If you do your titrations in the Sahara Desert or up in Antarctica where it's really hot or cold, you may have to adjust some of these things because Kw might be different. But assuming you're at room temperature, we're good to go. pKa plus pKb equals 14, just like pH plus pOH equals 14. I had a really good question earlier in my office. pH and plus pOH equals 14, like pKa plus pKb equals 14, but pH and pKa are different, all right? Like pH and pKa can be different because there's a ratio of the base and acid involved too. So pK plus pKb equals 14, pH plus pOH equals 14, but like pH plus pKb does not equal 14. You'd have different kind of results. Questions? All right.
When a molecule of hydrogen chloride and a water molecule encounter each other, they react to form a hydronium ion, H3O+, and a chloride ion. When sodium hydroxide enters the solution, it splits into sodium and hydroxide ions. The hydroxide ion and the hydronium ion react readily with each other to form 2 molecules of water. Sodium and chloride ions are left in solution.
hydrochloric acid becomes hydronium 100%. All right, you've got the chloride sitting around. Chloride is pH boring. It doesn't do anything. So HCl literally becomes hydronium 100%. And the same thing for the strong bases like sodium hydroxide. Sodium hydroxide quickly dissociates, the sodium ion goes away, and you have just hydroxide. So the real reaction between strong acids and strong bases is just hydronium plus hydroxide making water. And there's a lot of energy involved. Sometimes you'll feel the flask getting warm and stuff like that. Pretty crazy. So strong acid, strong base titration curves look something like this. They always start out acidic. Remember, the first thing that's listed is what you're starting with. So if you have just a strong acid, the pH will be acidic. And strong acids are usually very acidic. So pH 1-ish, give or take. It can go to 0, sometimes up to 2, but 1 is usually a pretty good place. And then the volume on the x-axis will be volume of the titrant, the second thing that's listed. So that would be a strong base. And bases make the pH get more basic. They will go up and up and up, all right? So this is a type of a titration curve you might see. There'll be a steep part, and it should be pretty obvious when it's strong acid, strong base. The middle point of that strong acid, strong base is going to be the equivalence point. So if you have a curve, you can literally just look at what you think is the midpoint of those points, and that's the equivalence. And it should be very close to 7, all right? In an absolute world, it would be definitely equal to 7. We'll see next week that sometimes calibrating your pH probe is a little bit more difficult than it might sound. But in theory, if everything's calibrated correctly, it will be equal to 7. So everything before that middle point of the steep point will be the pre-equivalence region, where the moles of strong acid are greater than the moles of strong base, and everything past will be post-equivalence. The moles of strong base now dominate over the moles of strong acid. So let's say that we have a pH of a strong acid, strong base titration. We want to know what the pH of the equivalence point will be. It says all these different possibilities. But what's happening with strong acid, strong base at equivalence? Anything going to be there?
Annihilation.
Annihilation, yes! I love that answer. Annihilation, absolutely. All the acid and base is gone. The moles are equal. They're 100 killers. They destroy each other, whatever you want. pH is going to be 7. No calculations. Yeah, I like the annihilation. Questions? It's not fun. You should be doing it right. Anyway, strong acid, strong base. This is something from your handout. It shows the 4 equations and stuff that you need. Now, none of these equations, to be totally honest, are super friendly looking. I completely dig that. But you will see patterns. You'll see things repeat, and that's what I want you to start seeing. So equivalence, pH is just 7, no problem. Initially, pH is going to be just the pH of a strong acid, minus log the concentration of the acid. You can write it as CSA, concentration of the strong acid, or you can write it NSA over VSA. And why that might be helpful is as you look down here further, there's NSAs and VSAs in the next one. And the first thing listed, those amounts will not change. So since you need them down here, sometimes it's easier to plug them in there. But on the other hand, if you have the concentration of strong acid of 0.1, you can go minus log of 0.1. Now at pre-equivalence, you have more moles of strong acid than you have strong base. So you essentially want to find out how many moles of your strong acid are left. But you do need to divide them by the total volume, all right? So it's always VSA plus VSB in the bottom. At equivalence, we talked about acid and base annihilate each other. I love that. So they just have pH of 7. But after you get to that point, then the strong base starts to dominate. And you want to find out how much base is left after the acid is gone. So this top part here is just finding out how much base you have left over. Still divide by total volume. Now remember, when you're doing calculations like this, initially you'll have maybe lots of pre-equivalence and you start having an error on your calculator. Anytime you have a log of 0, the calculator freaks out. So that is a good reason to go to the next equation. And this is just 1 point. So after that, you would go to the post-equivalence.
Do we need to remember these equations, like write them down in cheat sheet?
Yeah, I would absolutely put them down on your cheat sheet, you bet. There's 4 equations for the 4 types of titrations, and I would absolutely put them down. So yeah, sorry, I know it's not as much fun as watching paint dry, but they are important. And again, Donovan, at the end of the day, I can tell you any acid and base combination, you'll be like, oh, I'll find the pH using my equation. So that's my nerdy teaching rule.
Okay.
Good. That's a good question. Other questions? All right. So here's an example of hydrochloric acid. We're going to titrate it with sodium hydroxide. HCl, strong acid, sodium hydroxide, strong base. So the question is, what's the pH of your initial solution before any sodium hydroxide has added? Now, punchline is that pH is minus log of hydronium, and all of the strong acid goes to hydronium. So the punchline is you can just go minus log of 0.1 to find the pH. Here's a bunch of stuff saying why you can do this. First of all, just remember 5 strong acids, HCl, HBr, HI, HNO3, HClO4, 3 strong bases, sodium hydroxide, potassium hydroxide, lithium hydroxide. So hopefully you can recognize those. This is strong acid plus strong base. Notice we have volume and concentration of this solution, but we only have the concentration of the other one. So that means this will be listed first, the strong acid, because that won't change throughout the whole titration. The other amounts of sodium hydroxide will change, so that's why this is strong, SA+SB, strong acid plus strong base. Any questions, any of that? Okay. Here's the strong acid, strong bases. Once again, I know you're sick of it, but I keep talking about it. One-sided arrow, all right? So all the HCl goes to hydronium. So when you find the pH, minus log of hydronium, it's literally minus log concentration of strong acid. All of the HCl is turned into hydronium, minus log of 0.1, 1.000. This is a 3 sig fig concentration. When you do the log, the sig figs are the digits past the decimal, all right? So initially it kind of looks like I'm going from 3 to 4 sig figs, but the log means 3 sig figs would be 3 digits after the decimal. Any questions on that? Okay. Now, when you have so much of the second species listed in, you have to worry a little bit about if you're at equivalence, pre-equivalence, or post-equivalence. Now in this question, if you look carefully, the HCl and the sodium hydroxide are the same concentration. So if it takes 50 milliliters of 1.1 molar HCl, and we're titrating with 0.1 molar sodium hydroxide, how many milliliters of NaOH do you think it will take to get to equivalence here? If the concentrations are the same and you want the equal number of moles, volume in liters times moles per liter would tell you the moles. So one thing you could do to answer that question, divide this by 1,000, multiply by this number to find so many moles. And then moles of HCl will equal moles of sodium hydroxide at equivalence. So the moles of HCl divided by moles per liter sodium hydroxide would tell you how many liters and then milliliters you do. However, because the concentrations are the same, if we have 50 milliliters of HCl, it's going to take 50 milliliters of NaOH to reach equivalence. You can do it mathematically, or you can just kind of, if they're the same, it's going to be the same number. So let's pretend that you didn't know how many milliliters it was going to take to equivalence, which is totally fine. Finding the right region is important, and what you should do is solve for the moles of what you're starting with, which in this case is moles of HCl. So 50 milliliters becomes this many liters. Liters times moles per liter will give you moles. And that's all the moles of HCl you have, all the moles of strong acid. At equivalence, the moles of HCl and the moles of sodium hydroxide will be equal. And if you find the moles of strong base here, it's less than the moles of strong acid. So this one is going to be pre-equivalence. Pre-equivalence literally means that the moles of what you start with are greater than the moles of what you're adding, all right? So this is one way to verify that you're in the pre-equivalence region. If you're in pre-equivalence, minus log leftover moles of strong acid on top, and again, you'll get a non-zero, non-negative answer. Make sure you divide by the total volume on the bottom. Technically, this part right here gives you just one sig fig, so the pH in theory here would come out to be 2.3. Because you have more acid than base, your pH should be still acidic. But notice how when there was no sodium hydroxide, the pH was 1. And after adding 45 milliliters, which seems like quite a bit of strong base, it only went up to 2.3. Strong acids, wow, they fight hard. And strong bases too, for that matter. Any questions? Okay. Now, this question says, what's the pH at the equivalence point? And again, for this part now, you have to know how many milliliters of strong base it's going to take to get to the equivalence point where the moles are equal. At equivalence, you've got water and the conjugate ions, sodium and chloride ions. And the only thing that creates a pH there is water. And if water is totally pure, the pH is just going to be 7. So the nice thing about the equivalence point for strong acid, strong base interactions, always equal to 7, which is totally cool. Now, to find the volume of sodium hydroxide required to get there, what we're going to do is take that moles of strong acid that we found on the last slide, 0.0050 moles. And at equivalence, the HCl and sodium hydroxide moles are equal. So this moles is also equal to moles of sodium hydroxide. Moles per liter, if you divide by it, you can see how the moles of NaOH will cancel, and you'll have liters of sodium hydroxide left. So sure enough, it's going to take 50 milliliters of NaOH to reach the equivalence point. So that means that any volume past 0 and up to 50, you can use that pre-equivalence region equation. But at 50, that's when your calculator will spaz on you, and you've got to shift over to the pH of 7 value. Any questions? Okay, so at 55 milliliters, now we're past equivalence, all right? So we have more volume of sodium more moles of sodium hydroxide than we have moles of HCl. And because we calculated in the last one, it took 50 milliliters, and anything past 50 will be post-equivalence. So now your pH equation is going to look more like 14 plus log hydroxide. It's going to have a different form because hydroxide dominates. You've got to figure out how many moles of strong base you have. So again, sodium hydroxide still 0.100 moles per liter. 55 divided by 1,000 is 0.055. So moles per liter times liters, you're going to have the moles of strong base. And if all is said and done, now the numerator will not be 0, and it won't give you a negative number, which is what we have right here. Still dividing by total volume. It's 14 plus log now instead of minus log. And again, because the strong base dominates, your pH should be basic. 11.7 is basic. Yeah.
Is this only for strong bases and acids?
Yeah, that's right. This is for if you start with a strong acid and you slowly add strong base. Now we're going to see that like this equation is used in strong base plus strong acid, but what we're going through now is, yeah, good. Any questions? Okay. You can take these points and graph them. And if you need to make a graph, pH is the y-axis, and the volume of what you're adding is the x-axis. So this was a strong acid plus strong base. Sodium hydroxide will be on the x-axis. So initially, the pH we calculated was 1. At 45 milliliters, it came out to be 2.3. At equivalence point, like I said, is going to be 7. And after you get to that, it's going to be 11.7. Here's that steep region. It really shows on this graph right here. The middle point of it is where you should have the equivalence. And that middle point should be really close to 7. No problem. Any questions? Francisco asked about the acid base. This is the opposite kind of scenario. And it's strong base plus strong acid. And it's very, very close to strong acid, strong base. It's just that in this kind now, you're starting with a strong base, so your pH will be basic, all right? And as you add the acid, it gets more and more and more acidic. You'll have an equivalence point at 7 once again, and then post-equivalence, you'll start getting into acidic pHs. A lot of these equations will be copied and pasted basically from the last one. It's just that post-equivalence becomes pre-equivalence here, and the last one was pre-equivalence will be post-equivalence here. So I'm hoping that you're going to start seeing patterns. And these initial 4 times 4, 16 equations, a lot of them are going to be pretty chill when you start seeing the patterns. Anyway, the equations, here they are. Initial, pre-equivalence, equivalence point still 7, post-equivalence here. Now, post-equivalence here is the same equation as the pre-equivalence for strong acid, strong base. All right, what was more moles of strong acid makes it look like this, and that's what we saw in the pre-equivalence. Pre-equivalence here is the same as the post-equivalence right there, and pH is still 7 in equivalence. This one's different because when you have a strong base, pH is 14 plus log the concentration of the base. But again, my goal is that they'll start to look kind of familiar to you, at least a little bit anyway. Question?
Hydroxide ion is a strong base. It can be consumed in the body with a weak acid, such as dihydrogen phosphate ion produced in the kidney. In the reaction, an H+ ion transfers from the acid to the hydroxide ion to form water and HPO4 2- ion, the weak conjugate base of the weak acid.
In chemistry, there are thousands upon thousands of weak acids and weak bases. So a much more common analysis is the kind we're going to look at right now, where you have a weak acid plus strong base. Again, there's tons of these guys out there, so that's why they're really helpful. Several things will look similar here, but some things will look a little bit different. First of all, when you have a weak acid reacting with a strong base, that strong base annihilates, love that, annihilates the weak acid. And when the moles are equal, the strong base wipes out all the weak acid, but you end up with the conjugate. And a conjugate of a weak acid is a base. So the equivalence point for these kind of titrations will be basic. So if you have a titration and you don't know what exactly you were titrating, you can first of all tell if you started with an acid or a base, because the acids will start out low and the bases will start out high. And the second thing you can do is you can find out if it's a weak or a strong acid or base. So in this case, equivalence, this middle point of the steepest part, that equivalence point will be basic, all right? So those are some kind of cool things that you can do right there. Another thing we're going to talk about here is how half equivalence is pretty important. Half equivalence is where your pH and your pKa should be the same, all right? So Alana has found some new acids. No one's ever looked at them before. You can quickly then do a titration. That half equivalence pH should equal pKa, so she can find what the Ka values are from there and stuff like that. The buffer region is big time present in the pre-equivalence region, and that's why we've waited here to talk about these. That buffer region, it resists changes in pH, so it's usually very, very calm. The slope is constant, if you want to think about it mathematically. And we'll talk about that here in a little bit. Okay, so we've got a weak acid and a strong base. We put it together. We want to know what the equivalence point is going to be. Remember, equivalence point means that moles of weak acid equal moles of strong base. Those strong bases annihilate the weak acids. So is it pH equal to 7? No, good. What's left over when these two are equal? Base. That's right. That conjugate base kicks in. And it's a weak base, so it's not super strong, but what's important for us here is that equivalence point will be basic, all right? And that's different from strong acids, strong bases, or strong bases, strong acids. Weak acids create conjugate base. Bases will be basic, so that's why the equivalence point will be basic. Question? So, the equations, some of them look kind of familiar, some of them look kind of different. In problem set 2 this week, we talked about how for weak acids, if 100 times K is less than C, you can use pH equals minus log square root Ka times Ca, or Cwa to designate it's a weak acid. And that will apply 100% from now on. I'm just letting you know, all right, because it's by far the more dominant part. So if that's the case, minus log square root Ka times Ca will give you the pH of your initial point. Now, pre-equivalence, we're going to see, is a variation of Henderson-Hasselbalch. pH equals pK plus log, and we talked about how HH base over acid. We're finding essentially how much of the conjugate base is left on top, and on the bottom, we're going to see how much of the weak acid is left, all right? NWA is moles of weak acid, not the cool band that said the police. Anyway, prop that back on. It's moles of weak. Rory, you made my day. All right, if you know my reference I just made, that's cool. I'm a G-rated class. I won't say anything else. But anyway, Rory, thank you for seeing. All right, prop that back on. Aren't you glad it's Friday? Anyway, we'll talk about that later. Now, equivalence is the ugliest equation. Equivalence is the pH of a weak base. Now look, you could write here pH equals 14 plus log square root Kb times Cb, and that is equivalent. But Kb can also be Kw divided by Ka, which is why I have it written there. And concentration of your weak base is going to be the moles divided by total volume. I've written it this way for a reason. You're going to have Ka from before here, so sometimes it's easier. You don't want to find Kb explicitly. You can just go Kw divided by Ka. And the moles of weak acid, this number is going to be the same throughout. The volume of the weak acid will also be the same. So in this equation, if you know what the moles are, you literally only have to find the volume of strong base. So that equation looks kind of funky, I won't lie, but it's not too bad. But I say that a lot. You don't believe me at this point. I understand. Trust me, it's hopefully not good. Anyway, post-equivalence looks a lot like the post-equivalence between strong acid, strong base. The difference is in strong acid, strong base, it was NSB minus NSA, VSB plus VSA. If you put in the NWAs or the VSWAs right there, same thing. All right, so again, I'm hoping you're starting to see the patterns. If you have a strong base that dominates, 14 plus log leftover moles of strong base on the top divided by total volume. So these equations become quite repetitive after a while, which is the goal of what I want you to see here. Questions? So here's an example of a problem that you might see. Benzoic acid is actually a fairly common weak acid. It's a benzene ring with a carboxylic acid on it, C double bond OOH. This is the acidic hydrogen right there. And when it falls off, it makes the benzoate ion. This COO group right here can resonate that negative charge back and forth. It's somewhat common, doesn't matter. Anyway, Ka 6.3 times 10 to the minus 5, so you know it's a weak acid. Benzoic acid is not HCl, HBr, HI, HNO3, HCl4, so it's going to be weak. Question is, what's the pH of the initial solution? So what it's asking here, what's the pH of the benzoic acid by itself? And if you have a pH of a weak acid and 100 times K less than C, which it will be from here on in, you can use minus log square root Ka times Ca. I'm writing it Cwa here because it's a weak acid. So literally Ka, literally Ca, plug all that together, 2.90. Okay. Check yourself. It's a weak acid. It should be acidic. If you calculated a pH of 10 or something, which was greater than 7, look at it again. No problems here. Cool. Now, at the next part, we need to once again to know where that equivalence point is. And I mean, chances are this problem will be pre-equivalence, but it is always nice to kind of figure out. Remember, equivalence is where the moles of the benzoic acid will equal the moles of the sodium hydroxide. So what I would do here is try and find out the moles, all right, and compare them. And there's different ways to do this. But if you can compare the moles, that's the ultimate way to see where you are. So moles of weak acid, volume in liters times moles per liter, we have a total of 0.0025 moles benzoic acid. And at 10 milliliters of sodium hydroxide, 0.010 would be that liters. The concentration, 0.1 moles per liter, 0.0010 moles sodium hydroxide. Yeah.
Why did you do 0.01?
10, we have 10 milliliters, there it is, 10 milliliters of sodium hydroxide. That's a good question. So 10 divided by 1,000. Cool. All right, with these numbers, you can now see where you are. Moles of what you're starting with, the acid, are greater than moles of the strong base. So this is definitely a pre-equivalence region titration calculation. Any questions on this so far? Now, at this point, the strong base will lower the weak acid, all right? So the weak acid minus this number will tell us how much weak acid is left. But as much as it goes down, the conjugate base, the benzoate ion, is going to appear. And this is what makes these weak systems so strange. And even stranger is that because we have some benzoic acid left over and benzoate has been created, it is a buffer system. All right, it's going to act like a buffer. So that's why the HH equation is going to pop back into our world a little bit. Now, if you look at this equation, pH equals pKa plus log base over acid. And at the beginning of lecture today, I showed you an equation, pH equals pKa plus log, and on the top, it was moles weak base plus moles strong base, and on the bottom, moles weak acid minus moles of strong base. And that's where this equation comes from. The moles of weak base initially are 0, all right, so we don't worry about it. The moles of strong base will lower the weak acid, so it goes down. And as much as the weak acid goes down, the conjugate base will go up. So I'm just not throwing in there the NWB because we didn't start with any. It's being made by the strong base. That's kind of the idea going on here. Any questions on that? Okay. Minus log of Ka is pKa, 4.20. Plug and chug, use the moles, all right? Strong base moles, we calculated 0.001. Strong or weak acid moles, that number. All is said and done, pH is 4.02. Questions? All right. Now, 12.5 milliliters of sodium hydroxide might seem like a strange volume, but I'll show you why we're doing it. So from before, moles of weak acid, which have not changed, is that number, and pKa is that number. At 12.5 milliliters, which is 0.0125 liters, we end up with this many moles of sodium hydroxide. Still in the pre-equivalence region because moles of weak acid are greater than moles of strong base. So you can plug it into that equation. But a really interesting thing happens. At this point, the moles of strong base equal the moles of the weak acid that are left. So the moles of what we're adding are half of the moles of what we started with. And in the calculator, log of this number is like log of 1, which is 0. So at this point, pH equals pKa. And that's why this is so important if you have a weak acid or a weak base, because if no one's ever studied it, you don't have it on a nice table like we have in Brahm set 2 and 3, all right? You're the first person to look at it. So you do a titration. That half equivalence point might be the most important part, because at that point you can find the Ka. 10 to the minus 4.20 would give you the Ka value. Of course, it should come out to be this number, but that's why this is kind of cool. So if you have a brand new acid, cool. Questions on? Okay. Let's see. pH after that, yeah. This half equivalence region just means that pH and pK are the same. You can find the volume required. It's going to be twice the half equivalence volume. So if it took 12.5 milliliters to get there, it'll take 25 milliliters to get there. That's pretty chill. We will start with equivalence point on Monday. All right, thank you for being here, everybody. Have a wonderful weekend. See you on Monday.